Okay, let's talk about complex numbers. So consider for a second that there is a number that when we square it, we get -1. Well, then that would mean that that number, we'll call it I, is equal to the square root of -1. Okay, so it's kind of like here, if you started with I and you squared both sides, square rooting and squaring negate each other, and you're left with just -1. So, with that in mind now, let's go to what would I cubed be? Now, hold on before we go that far. You're probably thinking, hey, I've been taught in previous math classes that I can't take the square root of -1. And really what your instructor meant back then is it's not a real number. So we are going into an imaginary number realm. So we call these complex numbers when there's an imaginary part and a real part. So the math will still math. Okay, things will still work, adding and subtracting and multiplying and stuff. So we just have to keep in mind that when you see an I, unless told otherwise, it stands for the square root of -1. Okay, so now let's consider I cubed. Well, I could think of I cubed as I squared times another I. But I know I squared is -1. And I is the square root of -1. And since I don't like writing the square root of -1, I'm just going to keep it I. Now, if I wanted to simplify this or write it slightly different, I could say -1 or -1. I could say -1 times I or -I. Okay. Now let's go to I to the fourth. Well, there's two different ways we can look at this. We can look at it as I squared times I squared, which is -1 times -1, which we know to be 1. Or we could look at it as I squared twice, which is an exponent rather than writing it twice, right? So if we look at it as an exponent, a repeated multiplication, this would become I to the fourth, right? But we do know that this is a -1 to the power of 2. Same meaning, just a different way of writing it, resulting in 1. So whichever way. Okay, so now that we know that the square root of -1 is I, we can simplify into standard form. And when we mean standard form, they mean instead of having a square root of -1, we would write it with an I. So remember, radicals or square roots can get broken up as long as the operation is multiplication or division. So I can write this as the square root of, and underneath here, -1 times 25. I can break this up into two different square roots, square root of -1 and the square root of 25. Square root of -1 is I. Square root of 25 is 5. Because it's multiplication, I can break it up. Typically, we write the numeric piece of it in front of the I. So that's that one. Now let's go to the next one here, which is the square root of -24. So I'm going to break this up. -1 times 24. Now, the square root of 24 is not a nice number, so I'm going to break 24 up into a couple other numbers that one is a perfect square. So I'm going to do 4 times 6 because 4 is a perfect square. I know 6 can get broken up into 2 times 3, but neither one of those are perfect squares, so we'll just leave them. Okay, so now I have the square root of -1, the square root of 4, square root of 6, and all of them are multiplied together. Square root of -1 we call I. Square root of 4 we know is 2. Square root of 6 is not nice, so we leave it. And not nice meaning it's not going to be an integer or terminating decimal. It extends forever, non-repeating, right? So we are going to, we could leave it like that, and that would be fine. But oftentimes we write it number I and the square root of 6 on the back end. Now, I have had students in the past write 2 square roots of 6, I. And that's not wrong. Just be careful so that the I doesn't look like it's underneath the square root. If it looks like it's under it, then that's like saying square root of a square root, which is not what you intend. So the I is a square root all by itself already. Okay, so now that we did the stuff in the box, which is simplifying all these i's to different exponents, we can simplify something like this, where we have an I to the 32nd power. 8 happens to be just along for the ride. They're separated by multiplication, so 8's just there. Okay, now I'm going to take, since I know I to the 4th is 1, I'm going to try to get as many I to the 4ths as I can. Now I could write I to the 4th times I to the 4th times I to the 4th, but instead I'm just going to raise it to the power. I to the 4th, and if I do that 8 times, that's equivalent to I to the 32. Well, then this is 8 out front, negative 1, 8 times. Oh, I don't mean negative 1. Rewind. I to the 4th is a positive 1, 8 times. Oh, well, that's going to simplify to 8 times 1, and we just get 8. Now, I'm going to come up with a D here, part D. What if we had some number times I to the 33rd, and we wanted to simplify it and write it in standard form? Well, 5 also is along for the ride. I to the 4th, which we like because it's 1, I can repeat that 8 times to get I to the 32. But I have one more I that I need, so that'll go here. Because this is not enough, right? That's only I to the 32. So this is 5 times 1 to the power of 8 times I. Well, when I clean that all up, I get 5I. And I would much rather see 5I than 5I to the 33. So there's that. Okay, as mentioned a moment ago, complex numbers are imaginary. So we can write complex numbers with 2 parts if they have both parts. The first part is a real part. That's your real number that you're used to seeing, okay, in all the math you've done probably to date. And then we add the imaginary part on the back end of it. So if you saw the number 5 plus 2I, 5 is the real part and positive 2I is the imaginary part. Okay. Now we have here 3 minus 4I, and we're going to plot that on the complex plane. Well, a complex plane looks like a coordinate grid, right? You're used to seeing them with X and Y's. However, like plotting a 2, 1 or whatnot. But when it's a complex plane, the horizontal axis stands for the real numbers. So in this case, the real number is a positive 3. And the imaginary part is negative 4I. So we are going to go positive 3 in the real numbers, right? There's where my positive 3 is at. And then you're used to plotting coordinate points, and now just the vertical is the imaginary. So anything on the vertical stands for the imaginary piece. So a negative 4, 1, 2, 3, 4 is here. And this point right here stands for 3 minus 4I. Okay, here's something that's unique to complex numbers. We consider this one complex number, but there's 2 pieces to it. So when we plot using the 2 pieces to plot the one number. All right. Operations with complex numbers. Here's the very nice thing about operations with complex numbers. You can treat I, for the most part, like a variable. The only time you have to do additional work because it's imaginary is if you get an I squared, I cubed, I to the fourth, I to the 33rd, if you will, stuff like that. So for this first one, when it says add, essentially, okay, when we're adding, here we have 3 minus 4i plus 2 plus 5i. There's nothing to distribute, so it's 3 minus 4i plus 2 plus 5i, and we add the like terms together. So the 3 plus 2, we get 5. The negative 4i plus 5i will make it a plus 1i. And there is the result of adding them together. All right, subtract 2 plus 5i from 3 minus 4i. So we have to start with the 3 minus 4i because that's where we're coming from. And we're subtracting 2 plus 5i. I will need to distribute now this minus sign. So this will be 3 minus 4i minus 2 minus 5i. Combining like terms now, we get 1 minus 9i as an end result there. Multiplying, here we're just multiplying a single number times the quantity 2 plus 6i. So again, this is just like the algebra you would have seen before. We'll distribute 8 plus 24i. Multiply these, again, very similar to what you've done before. I'm only going to note that when we get an I squared, we'll have to simplify that. So remember how you used to do this multiplication. First, we're going to distribute the 4, and then we come back and we distribute the 3i. Okay, some people like to use FOIL, which is basically doing the same thing. So distribute your 4, 8 minus 20i. Now I'm going to come back and distribute my 3i plus 6i minus 15i. And it'll be 15i squared because you had 3i times negative 5i. So 2i's I squared. Now, remember from above, I squared was equal to negative 1. So this becomes 8 minus 20i plus 6i minus 15 times negative 1. That's going to turn that into a plus 15. So we got 8, I'm going to combine these two, minus 14i, and then plus 15 on the back end. So in the end, we have 23 minus 14i. All right, dividing is where things get a little bit tricky. If I have 2 plus 5i and I'm dividing it by 4 minus I, the trick for dividing, and let's go up to this box or the top here where I mentioned it, we are going to actually multiply numerator and denominator by the denominator's complex conjugate. Okay, well, what's a complex conjugate? The complex conjugate has the same real part and the opposite imaginary part. So a plus bi, a minus bi are complex conjugates. So I am going to multiply the top and the bottom by the denominator's conjugate, 4 plus i. 4 plus I. Now, remember there's parentheses here and here, whether we should just make a habit of putting them in there. All right, so that means now that we need to basically multiply the top out and multiply the bottom out. I'm going to do the bottom first because that's where the fun is. That's where the trick is to this. So we're going to distribute the 4 first. 16 plus 4i. Now I'm going to distribute the minus I. minus 4i, a minus I squared. Okay, I'm going to go one more, and then I'll do the top yet. Just bear with me. These are opposites. They negate each other. This is a minus I squared, but we know that that means it's going to be a minus -1. So in the end, I have a 16 plus 1 for a denominator of 17. So the doing that cleaned up the bottom, and we didn't have square roots in the denominator, right? Because I is a square root, and they don't belong down low, so that's one way to do it. Okay, then the top, we'll clean up the top here. Distribute the 2, 8 plus 2i, distribute the 5i, plus 20i, plus 5i squared. This will turn into 8 plus 22i plus 5 times a -1. So that really is going to turn that into a -5. So in the end, in the numerator, we have 3 plus 22i. Okay. Moving on, we can plug i's into functions just like we would plug numbers into functions. So here, if I have f of x is equal to x squared minus 5x plus 2, and I want to plug in 3 plus I would say this is 3 plus I squared minus 5 times 3 plus I plus 2. Clean up. This is 3 plus I, 3 plus I. So I'll have to distribute that out. This is going to be a minus 15 minus 5I. And then there's a plus 2 on the back end. So here for this distributing, 9 plus 3I plus 3I plus I squared minus 15 minus 5i plus 2. And now it's just a lot of cleanup there. So in the end, f of 3 plus I is equal to my -6, 3, 6 plus 1i. I have a 2, and then I have that is a -1, right? So I'm adding a -1 there, so it's going to be plus 1. So -5 plus I is what we get in the end. F of 3 plus I. There we go. Okay. Next, evaluate this one, g of 10i. So that means how it's a plus bi, that means that you have 10i there, and the a part or the real part is 0. Okay, I don't have to put the 0. Just know that that's what that means there. So if I'm going to do g of 10i, this will be a 2 plus 10i over 10i plus 3. Ugh, I can't cancel, right? You can't cancel. Not unless it's all multiplication, and it's not. There's additions there. But I'm going to rearrange the order in the denominator here. It's going to be 3 plus 10i. Can't cancel. What I can do to clean this up for the simplifying piece is I have to multiply by 3 minus 10i, 3 minus 10i, because it's the complex conjugate of the denominator. Denominator, 9 minus 30i plus 30i minus 100i squared. Well, we know I squared turns this entire term to a plus 100. Those negate each other. So in the end, our denominator is 109. The top, distributing the 2, 6 minus 20i, distribute the 10i, plus 30i minus 100i squared. This part becomes a plus 100. So I'll have 106 plus, and then these two i's, when I combine them, 10i. All right. Now, why are we learning all this stuff? Well, we're learning all this stuff because as we continue on with the course, we might have situations where we end up with a negative underneath a radical. I'm going to show you an example of when you may have seen it before, but we're told, no, that just means don't worry about it. Okay, well, now you're going to worry about it. Solving quadratic equations. Normally, we would use the quadratic formula or factor or complete the square, right? We had all those you learned in the previous math class, all these ways to solve quadratics. Well, remember this way. If you have a quadratic and it's equal to 0, the solution is x equals opposite of b plus or minus the square root b squared minus 4ac, all of that over 2a. Okay, so looking here at this quadratic, here's my a, here's my b, here's my c. X is equal to the opposite of b plus or minus the square root b squared, positive 25, minus 4ac, all over 2a. Okay. Here I have 25 minus 52, 26, 20, yeah, 52. And then all over 26. Now I have to do the subtraction there. 52 minus 25 is going to be 27. So we have 5 plus or minus the square root, and it's going to be a negative 27 under there over 26. Now, 27 is 9 times 3. 9 is a perfect square, so we'll break it apart, just like we did prior. So I'm kind of running out of room here. I'm going to move down. X is equal to 5 plus or minus the square root, and we have a negative 1 times 9 times 3. And all of this is under 20 or over 26. Now, I know the square root of negative 1 will be I. The square root of 9 is 3. And then the last 3 I can't do anything with. So the answer here is 5 plus or minus, square root of 9 was 3, I times the square root of 3. I don't like putting the i's on the back end because I don't want it to look like it's under it. And both of these are over 26. Now, there are two solutions to this quadratic, but they are both complex numbers. One is 5 plus 3i root 3 over 26, and the other one is 5 minus 3i root 3 over 26. So now we can manage and work with getting negatives underneath square roots. And when you were solving quadratics like this and you were looking for, say, intercepts, I can tell you right now that this quadratic, right, would graph a parabola. And the fact that there was no real places where it equaled 0, there's no x-intercepts, right? So hopefully you kind of learned that in a previous course, that when you get a negative underneath there, it means that there's no real x-intercepts. So, all right, that concludes this section.